Okay, so today we're going to be kind of shifting gears to mostly grade 11 stuff from here on out. So you've heard me mention a lot of times, like when people were asking me, like, do we need to leave this in fraction form or whatever, that in this course we're going to be spending some time looking at ways that we can express things as exact values. So this is kind of our first step into some of that, other than obviously like working with fractions, is simplifying these things called radicals. And we do this just so that we are able to actually leave things in exact values, because a lot of times we don't get actual exact answers when we go and evaluate these radicals. We'll get like decimals that go on forever. So our goal is to be able to express a value exactly without having to round or do anything like that. Okay. So firstly, we need to know what is a radical. So essentially, it's going to be anything underneath a root. So this whole thing is called a radical. And then the value underneath a root, so in this case n, is called the radicand. Okay, in order to work with radicals, we also need to know what are perfect squares. And we've talked about this a little bit when we talked about like difference of squares and perfect square trinomials. Does anyone remember what I mean when I say perfect squares? GD? So, close. So I think you're thinking more like perfect square trinomial, but what is just a perfect square? You think that you know? Pardon?
It has to be multiplied by itself.
Okay, so the value should be able to be square rooted and give us a whole number, right? So if I wanted to generate a list of perfect squares, I can just do 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, 5 squared, 6 squared, and so on. So we're going to generate kind of like an initial list here. Anytime you're working with radicals, I would suggest that you generate this list. Again, all I need to do is just on my calculator go 1 squared, and then 2 squared, 3 squared, 4 squared, and so on. So 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, and I think that should be enough. But we know we of course can go on and on with this list if we want. Oops, sorry. So the list continues on forever. We could generate an infinite list of perfect squares. Okay, but for now I think that that's probably enough. So always good to write out this list of perfect squares while you're working with radicals. Okay, so the first thing that I'm going to show you is how to simplify a radical and express it as what we call a mixed radical. So you guys know, like, when we're working with fractions, the idea is if I have some work that I've done and then I get out 2 over 4, we always simplify that to 1 over 2, right? So similar to how we want to reduce fractions, we also want to reduce radicals, but we do it obviously differently than we reduce fractions. So part of what we need to use is this list of perfect squares. And the goal here is to split up the radicand, or the number underneath the root, into, if possible, a factor that is a perfect square and any other number. And not only just a perfect square, but the biggest perfect square that can divide into the radicand value. So when I say factors, I just mean like things that multiply to give you 27. So does anybody see anything in this list that will multiply to give us 27 with something? Olivia? 9. 9 times what? 9 times 3. Okay, so we're going to split 27 up into 9 times 3. I always write the perfect square part first. And there's this cool little rule with radicals, and it says if you have a product of 2 things underneath a root, you can actually write them as the product of the individual square roots, and those 2 things are equal. And so I can actually square root now this perfect square part. What's the square root of 9? 3. So I can actually write this as 3 root 3. That's how we simplify a radical. Okay, and now we've written this as a mixed radical. So you can do a check on your calculator. If you sub in root 27 and figure out what the decimal value of that is, it should match what the decimal value is of 3 times root 3. Okay, some of your calculators, if you plug in root 27, it will actually even show you that it's equal to 3 root 3, but now you know why that's simplifying to 3 root 3. Okay, so I know that your calculator knows how to do it, but I want to know that you know how to do it. So I would expect to see at least one of these 2 steps in between to show me how you got from 27 to 3 root 3. Okay, let's go over to number 2 here, 50. So 50 is not a perfect square in and of itself, but does anybody think that they can see a factor inside of 50 that is a perfect square? Cameron? 25 and what? Multiply by 2. Perfect. So we can split these into their own roots. It's a property of radicals. And then just evaluate the square root of 25. So 5 root 2. Okay, again, if I check the decimal value of the square root of 50 and the decimal value of 5 times the square root of 2, those 2 things should be the same. Okay? So if you want to do a check, you can check that the decimals are the same. Okay, getting a little bit bigger here, 180. Olivia? Ooh, 36 and 5. Okay, why wouldn't I choose 9 and 20?
Because you can't see what we can.
We could. What do you think, Olivia? Okay, so if I chose, let's just say, you guys don't have to write this down, but let's just say I chose 9 and 20. You will notice something about this second value. What do you notice about 20 as far as the list of perfect squares? Are there any factors still inside of 20 that are perfect squares? 4 is inside of 20, right? 4 times 5. So if my second value here still has perfect squares inside of it, I haven't found the biggest perfect square. So rather than using 9 and 20, there's a bigger number that actually is a perfect square that divides into 180, and it's 36.
So always use a bigger number?
Always, we're trying to find the biggest perfect square. Yep. Okay, so we said 36 and 5 should work for this one. And we're going to split these into their own radicals. And then just root the perfect square part. So we get 6 root 5. Okay, so I know that 36 is the biggest perfect square because if I look at 5, there are no more perfect squares inside of that other than 1. 1 it will always be obviously divisible by every number, or a factor of every number, I should say. So we always want to make sure that this second value that we put doesn't have any factors inside of it that can be reduced further. Okay, so that's the first thing. That's simplifying radicals into mixed radicals. Any questions so far for this? Okay, for 50, why couldn't I use 5 times 10?
Because 10 is only like divided to 2 and 5, so there's none of them like a perfect square.
Yeah, 5 is not a perfect square and 10 is not a perfect square. So one of those 2 things, if I'm going to split the value up into 2 values, one of those 2 factors has to be a perfect square. Okay? Not every radical can be simplified. Okay? So if I have something like the square root of 61, there are no factors of 61 that are perfect squares. So this is the furthest that I can go with this. It's just root 61, that's all. Okay, just like if I have a fraction 3 over 5, that's the furthest I can go with it, right? I can't go any further. Okay, when we are multiplying radicals, okay, so we can do operations with these things as well. I like to think of these kind of like in pieces. So you're going to multiply the numbers that are out front of your radicals together. So 4 times 5, that will give you 20. And then you're going to multiply the root parts together and keep them underneath a root. So root 6 times root 3 is root 18. Okay, so multiply, I like to kind of call them like the coefficients of the radicals. Multiply the parts out front, and then you're going to multiply the roots. Okay, and then what we're always checking anytime we do operations with radicals is if I can simplify what's in the root. So are there any perfect squares inside of 18? 9 and 2. Okay, and then I can actually square root the 9 part of this, so I'll write it as 3. And I can actually simplify what's out front here. 20 times 3, that just gives me 60 root 2. Okay, again, I can check my answer and I can make sure that the decimal value of this is equal to the decimal value of this. Or if your calculator calculates it for you, you could always plug this into your calculator and it should give you out 60 root 2. Okay, that's a way that you can check, but I do want to see most of this work from you to show that you know where it comes from. Any questions on that one? Okay. 5 root 2 times 6 root 10 times root 5. So when you see a single root 5, you can think of it kind of like 1 root 5. So I'll do 5 times 6 times 1. That will give me 30. And then I'll do root 2 times root 10 times root 5. So that will give me root 100. Okay, what do you notice about the value 100? This is a special value. It is a perfect square. So do I know what the square root of 100 is? It's just 10, right? I don't have to split 100 into anything. I can just square root 100 and I'm going to get 10. So anytime you square root, anytime you see a perfect square underneath there, just square root it. You can just evaluate. So here we're left with 300. Okay, sometimes we get like so caught up into like, what can I split this into, that we don't realize that we can actually just square root the value. So look out for those. So far so good? Okay, can I scroll? Okay. All right, adding and subtracting when we're working with radicals. All right, you guys have actually done something like this before in grade 9. So you guys actually already know how to do this. Let me ask you this. If I told you 3x minus 5x, what would you tell me this is equal to? Negative 2x. It's no different with radicals, okay? So only things with the same radical value can be added or subtracted. So for instance, when you guys were in grade 9 and you had to do something like this, can I put those two things together? Why not? One's an x, one's a y. So if I have two different roots, like a root 2 and a root 7, those are completely different. I can't put them together. But if I have two of the same root, just like if I have two of the same variable, I can put those together, no problem. So in the first one, you'll notice we have both of these ending in root 5. So if I take 3 root 5s and I subtract 5 root 5s, I'm left with negative 2 root 5. Just like when I do 3x minus 5x, I'm left with negative 2x, right? And is 5 fully simplified?
Yeah.
There's no perfect squares inside of 5 other than 1, obviously? Okay, so that one's good. Okay, at first glance, you might say, I can't add root 54 and root 6 together. However, if we simplify, we might be able to. So are there any perfect squares inside of 6? No, so that one stays as 8 root 6. What about 54? What's the largest perfect square inside of 54? 9 times what?
6.
9 times 6, perfect. So we're just going to simplify this a little bit. I'm going to square root the 9 part, that's 3. And the 6 stays under the root. And then I'm going to just follow BEDMAS here. So I'm going to multiply 3 times 3 first to get 9. And then I can add.
So be 17.
So 17 root 6. Perfect. So 8 root 6s plus 9 root 6s means I have 17 root 6s.
You don't add the roots yet with a sign.
Yes, don't add the roots. Just like I don't duplicate the x's or anything, right? You keep the last name and add the numbers in front. So keep the root part, add the numbers in front. Any questions on those two? Okay, and then last part here is simplifying rational expressions, so expanding and simplifying. So this is like distributive property, what you've been doing in grade 10, all of that kind of good stuff. Can you put your phone away, please? Thank you. Okay, so this root out here, 12 root 2, needs to be multiplied by both things inside here. Okay? So by this, so essentially, yeah, we're doing FOIL, but I mean, this one's not two binomials. So we're going to do kind of like FOIL, yep. We're going to do 12 root 2 times 2 root 2. Okay, so ignore this for a second. We're just going to do 12 root 2 times 2 root 2. So 12 times 2 is 24. And root 2 times root 2 is root 4. Okay, so you multiply the numbers in front together, multiply the roots together. Okay, then we're going to ignore this middle part here. So we're going to pretend that this isn't here. And we're going to do 12 root 2 times, like I said, you can pretend there's a 1 out there if that makes you happy. 12 times 1 is 12. And root 2 times root 6?
12.
Root 12, yeah. Okay, so that's the first one, and then that's the second one. Okay, you need to see if there's anything left that can be simplified in those two radicals that you simplified. So what do you notice about this?
It's root 2 times 2.
Yeah, it's just a perfect square. Can I just write 2 for the square root of 4?
Oh, it's 4.
Yeah, for sure. And we do have a 4 inside of 12, so 4 times 3. So we can simplify this. 2 times 24 is just 48. And then I'm going to root the 4 here. That's 2. And then we're just going to simplify out front here by doing 12 times 2. That's 24 root 3. Should I add 48 and 24? So if I have 48 plus 24x, I don't add 48 and 24 together, right? So if I have 24 root 3 and 48, I can't actually add those together. I can add 48 root 3 and 24 root 3, but I can't add 48 and 24 if the 24 has a root 3 on it. Okay, so this is actually our final answer. Okay, any questions on any of the steps here? How did you go from this step to this step? Where did this number come from? Anything at all? We're all okay? Okay, let's try one more. We're going to do FOIL with this guy. So we're going to do firsts.
Power to FOIL, Judy.
Okay, so just focus in on these two right now. I want to do 2 root 3 times 5 root 7. So we're going to take it slow for this one. 2 times 5. And root 3 times root 7 will be root 21. Perfect. So we get 10 root 21 for the first ones. Okay, then we're going to do outsides. So we're going to do 2 root 3 times positive 8 root 5. So 2 times 8, it's going to be positive, firstly. 2 times 8, 16. And root 3 times root 5, root 15. Perfect. Halfway there. Okay, now you're going to do insides. So negative times a positive, I'm going to get a negative term as my next one. 3 times 5 is 15, yep. And root 5 times root 7, root 35. And lasts. So here we have a negative times a positive. We're going to get another negative term. We'll do 3 times 8, which will give us 24. And root 5 times root 5, root 25, right? Okay? Look through. You need to check all your radicans and see if any of them have perfect squares inside of them. So 25 is in and of itself a perfect square, right? So we should be able to simplify 25 just to 5.
So can we simplify it to, so will we multiply 24 by 5 then?
Yes, we will. So on the next step here, I'm going to simplify 24 times 5. Okay, is there anything else that needs to be simplified or no? No, I don't think any of these have perfect squares inside of them. So what do we get here? 120? Negative 120? Okay, and are there any like roots that we can add together? No. So we're done here.
Then why are we done?
Because we can't go any further. What else would you do? Okay, any questions on this one, guys?
Is this like exponent laws?
Not really.